Yeah, so I would like to give a quick update on the status of the massive survey with an emphasis on supermassive black holes, since that's the theme of this section. And this survey was started really, was motivated by about 10 years ago when we used Gemini GMOS along with wide field IFU data to find a black hole that was 3 times more massive than M87 at the center of a very big galaxy, well-known galaxy, NGC 4889, which is the brightest cluster galaxy at the center of the Coma cluster. And, this is the most massive by stellar mass galaxy in the local volume. And Coma is the spectacular, most massive cluster in the northern sky out to 100 megaparsecs. So it was not, in some ways, not too surprising, as we have heard, that big black holes live in big galaxies. So the environment wasn't so surprising for detection of such a big black hole. But it was hard to get data with enough sensitivity and modeling to actually detect a black hole. So after this discovery, a natural question was, how many of these things are out there? What is the, number density? And can we maybe get a mass function for black holes at a very massive end in the local universe? So that sort of motivated the start of the massive survey. I'm having some trouble advancing the slides.
In the practice,
could you just help me?
Yeah, in the practice you clicked and then you were able to move.
Yeah, I tried, but okay. We'll see how far we get. Okay, so the massive survey is a detailed study of the 100 about most massive galaxies by stellar mass within this volume out of Coma. And very importantly, we targeted these galaxies using a mass limited survey. So it's volume limited, and we use K-band, 2 mass K-band magnitudes as a proxy for stellar masses. And so all the galaxies have stellar masses above 10 to the 11.5, and we target only early type galaxies. And the deck cut was -6 degrees, so it's mostly a northern sky survey. And we really want to study not just the supermassive black holes, but all mass components within these early type galaxies, stars, of course, and cold, warm, hot gas, dark matter halos, and the black holes. And we've involved many graduate students along the way. And in particular, we're very excited that we've trained more than 10 undergrads and high school students in getting their hands on analyzing IFU data and doing analysis and so on. And there are a few offshoots of the massive survey with emphasis on, for example, the HST photometry, where we targeted 35 galaxies within about 80 megaparsecs, for which we can obtain surface brightness fluctuation distances. The black hole measurements are only as good as the distances we can get, because we can only measure things angularly on the sky. So we need precise distances to convert anything into a physical number, such as the black hole mass. So this project was led by John Blakesley and Joe Jensen. And so along the way, we actually were able to actually get a new measurement, the most comprehensive measurement of the Hubble constant, H0, using SBF technique. And also we were curious about a molecular gas and X-rays, hot halo we heard about, and also the initial mass function possibility of a steepening near the center of these massive galaxies. And so these are all different components of the massive survey led by various people. Okay, so why study nearby massive galaxies? Just very quickly, we have heard a lot about these objects. So they are the most evolved galaxies, and because they're most massive, they're at redshift 0 practically. So they carry, in some sense, the most amount of historical information of galaxy assembly. And they are obviously hosts of the most massive black holes. And we heard a lot about luminous quasars, and some of those should have descent into the quiescent counterparts today in massive galaxies. And these are sites of AGN feedbacks and IMF, as I mentioned, variations in the IMF spatially. And also, as we also heard from Xin Lu, that if they're in binaries, they are the loudest sources of low frequency gravitational waves. So these are potential hotspots on the sky. And why another galaxy survey? Haven't there been enough galaxy surveys? Well, you would think, right, these are the 100 most massive galaxies in our backyard, these 300-pound gorillas should have been studied very well by now. Well, interestingly, actually only about 2/3 of the massive galaxies are in the SDSS footprint. Our galaxies are chosen from the All-Sky Survey 2 mass. And spectroscopically, only 20% actually have SDSS spectra. And remember, SDSS is just a single fiber of 3 arcseconds, but we would like to have a really well spatially resolved IFU data to study the interior of each galaxy from sub-arcseconds out to about 100 arcseconds. And we heard about Sauron Atlas 3D survey. So in that sense, for that survey, we are very complementary. They were also volume limited, but and they were studying early types, but their volume was 42 megaparsecs. So our volume is more than 10 times larger, and hence since we are targeting the 100 most massive galaxies, we are very complementary. In fact, there are only 6 overlapping galaxies in our 2 samples, and those are mostly in Virgo because many of their galaxies are in Virgo. And there are, of course, many exciting IFU surveys ongoing, but their samples are heterogeneous. Sometimes they impose size cuts and various selection cuts. We just don't, we only select based on stellar mass. And also we are very multi-wavelength, and one of our essential science goals is to study black holes, and none of those surveys target black holes. Okay. And actually not all of the massive galaxies are BCGs, and they in fact live in a diverse range of environment. Okay, so I want to just focus on black holes for the rest of the talk, but I would like to just highlight, in case you're interested in other pieces of science from the massive survey, here's a list of the publications, and we have some of the ones I've mentioned, and I will from this point on just focus on the how we go about measuring black hole masses in our current results. And Janelle had already mentioned, but just as a cartoon version of the very messy data we have been collecting over the past 3 decades. So again, a central question we're asking is, are there things beyond M87? And yes, NGC 4889 was the first one discovered in the local universe, but the massive survey is meant to target this systematically. Okay, and indeed, NGC 1600 on the left was or is a massive survey galaxy, but it's not a very well-known galaxy in comparison to NGC 4089, but its stellar mass is high enough to be in the massive survey. And we got sufficient high signal to noise data from both GMOS and Mitchell spectrograph on McDonald telescope and McDonald Observatory, and that allowed us to find this 17 billion solar mass black hole, but in a sort of an event massive galaxy which does not live in a rich cluster. NGC 1600 is sort of a, is a galaxy group, but the second rank, the second next brightest galaxy is 3 times fainter than NGC 1600. So it has sort of the characteristic of a fossil group. It doesn't quite satisfy that particular criteria, those criteria people laid out, but the gap is very large. So one interesting question comparing these 2 very massive galaxy black holes is that they have comparable masses, but they live in quite different environment. So this again motivates further studies to see, is NGC 1600 just the tip of an iceberg, because the halo mass, is much smaller than the coma cluster, so they should be more abundant. But so it could be a tip of an iceberg, or perhaps this is a very rare object because of maybe galaxy mergers or something that 1600 ate up its neighbors in its evolution history and hence grew to such a high mass black hole. We currently don't know the answer. More data are needed. Obviously, simulations are helpful for answering these questions. Okay, so we have heard about the velocity V, the velocity dispersion sigma, which are the bread and butter kinematics everybody measures. But as Janelle mentioned, for black hole measurements, it's critical to get the full shape of the velocity distributions of the line of sight stellar motions. And we really need a skewness, so we cannot assume Gaussian, but we would like to get a skewness, H3 shown here. Kurtosis, the boxiness, peakiness of the distribution for each spatial bin, H4. And in fact, here I'm showing you a GMOS data of the 5x7 arc seconds on the sky of this massive survey galaxy is a fast rotator, NGC 1453. In fact, the signal to noise is so high of about 100 that we're able to measure out to H8. Of course, when you get to the higher moments, the numbers are consistent with being 0, but we think it's quite critical not to truncate these velocity moments, but rather include them and constrain the stellar orbit models using these moments to avoid spurious behavior in the stellar models. And we discuss a lot of these details in our papers. Okay, and here are some of the real crucial ingredients we need for the spectroscopy. Okay. And GMOS really is incredible for providing us with the central stellar kinematics that are inputted into the stellar models. Okay, so before going further with the black holes, I would like to just showcase concentrating on sigma, the velocity dispersion, the second moment of the stellar. Again, these are all absorption line features. And here is a compilation of the 20 galaxies. And right now, we're just targeting 20 out of the 100 massive galaxy with GMOS and all necessary data for black hole measurements. And here you are seeing sigma profiles for 20 galaxies as a function of the radius from the center of each galaxy. But note that we have plotted the radius in logarithmic scales because we have our data encompasses 2.5 dex coverage. And the magenta is again from GMOS, and the green points are from the very wide field McDonald-Mitchell IFU. And I want to just showcase that we often like to assume, like, for example, in gravitational lensing studies, sometimes, right, we assume the sigma is an isothermal profile, i.e. flat, as a function of radius. You can see when you have very detailed IFU studies, nothing is flat. In fact, 40A74, this is the twin of 4089 in coma, has this very interesting rise at the outer part in sigma. And this could be that we're starting to feel the dark matter contributions there. Okay, so these are, there's a rich amount of information here just in sigma profiles. And let's look at the just the first moment velocities. Okay, that's also critical. And here, again, I'm showing the GMOS velocity maps of 20 massive galaxies. One key discovery we had, or outcome of these 20 galaxies, is that we are able to measure, as you can see, the velocity kinematic axis, the rotation axis. And you can see that the black indicates the photometric axis. So for some of them on top here, including NGC 1700 that we heard about, they are quite well aligned. On the other hand, at least half of them, the kinematic axis is not along the photometric major axis. That is to say, it's not rotating, the galaxy is not rotating about the minor axis of the photometry. And this is well known as a kinematic misalignment. And here we're showing the distribution of this misalignment angle. And one of the Sauron Atlas 3D's main results was that early type galaxies are fast rotators and they're quite well aligned. Now that's for lower stellar mass early types. For our mass range, early type galaxies, you can see there's a long tail of misalignment, in fact, all the way to 90-degree misalignment, indicating that the galaxy is rotating actually about the major axis, so-called polar rotations. So this by itself is very interesting for galaxy assembly people to study, but one important implication of the misalignment is that these galaxies are triaxial in shape. Okay, but before I go on, I just want to highlight NGC 1700 that we heard about has a beautiful counter-rotating stellar core here in the GMOS V velocity map. You can see the outer part is blue-red here, but the very center has a red and blue. Okay, so following up on my comment just now, because absolute axisymmetric galaxy cannot produce kinematic misalignment from the photometric axis. So necessarily they have to be triaxial in shape, meaning, the three principal axes shouldn't be of the same length. So the implication for the black hole modeling is quite deep, because most of the earlier stellar dynamical results for the black hole measurements assume either spherical or axisymmetric gravitational potential. As Janelle mentioned, M87, the stellar dynamical measurement of 6 billion solar masses by Gebhardt et al. Assume axisymmetry. But what we have learned so far is for galaxies as massive as M87 or those in the massive survey, they're very probably going to be triaxial. So we have been spending probably the past 2-3 years really focusing on getting a more efficient Schwarzschild stellar orbit code to work. And we named this the TRIAS code, and it's based on the Remco-Van Bosch 2008 code. And here, just for some details for the implementations we have added to revamp the code. And triaxial orbits are much more expensive to compute because of these additional stellar orbits called boxed orbits we must integrate. So the whole modeling part for dynamical black hole measurements is becoming more expensive. Another key part is the search strategy, because now we are simultaneously modeling black hole mass, stellar mass to light ratio, dark matter parameters, and now we have 3 shape parameters, A, B, and C, to simultaneously search for. So we can no longer use grid searches, and we are doing Bayesian machine learning algorithms. We're introducing those to speed up the search. So I just want to showcase our 2 recent measurements, and we have targeted the 2 and only 2 very fast rotators in the massive survey. Among the 20 galaxies, we have complete data sets for dynamical measurements. And NGC 1453, as you saw, it has a rotation about 100 kilometers per second. So V over sigma is still, small, about 1/3, but it's a fast rotator by comparison. So here we were able to search in these parameter spaces, and you can see our final result, the corner plot. So we are able to determine the black hole mass is about 3 billion solar masses. So it sits on the M sigma relation. And also we are able to measure simultaneously the intrinsic triaxiality of the galaxy through Schwarzschild modeling. And here I want to just highlight, this is the P is the intermediate to the major axis ratio, and this Q is the minor to major axis ratio. So you can see it's 0.93, so it's slightly flattened, but the short to long axis ratio is flattened by quite a bit. Okay. So just a second example, another fast rotator, as you can see in our velocity maps here. Again, GMOS, beautiful data from GMOS. It's rotating at more than 100 kilometers per second in the core of this galaxy, and we combine this with the Mitchell data. And again, it's about 1.7 billion solar black hole, and we are able to measure the axis ratio. So I think it's very hard to determine the intrinsic shape of a galaxy, obviously. And this technique, through rich set of kinematic and photometric data and extensive dynamical orbit modeling, enable the determination of the intrinsic shapes in addition to these mass parameters. Okay, so I just want to just summarize our ongoing efforts here with the massive survey and beyond. So again, the triaxial we are introducing, we have also put in master light gradients, spatial gradients. I'm happy to talk more about this privately. And these are various things we're working on the modeling theory part. Observationally, we still have 18 of the GMOS galaxies that are now slow rotators, and this is made triaxiality even more important here. And we're exploiting other high sensitivity IFUs and also comparing different dynamical tracers. And we're very excited about the M87 JWST data Janelle mentioned. So just concluding thoughts, again, the sort of the takeaway messages here are that direct local dynamical black hole measurements, so I don't mean quasars or AGN, the width of the emission lines, but here is really detailed modeling. As you've seen, they are very difficult. It comes in one by one, but they really are the low rung of the black hole mass ladders, right? All the reverberation mapping, AGN, quasar, black hole mass estimators rely on calibrations. The virial coefficient has to be calibrated to local measurements. And the black hole world and the local universe have come a long way. The two well-known, best studied black holes have been known since pretty much the late 1970s. And as we heard, the 1990s were the glorious days of using HST slits to measure black holes. But now I think the past decade or so, we've moved to the large ground-based telescopes because of the high sensitivity we need. But combined with IFU and AAO, we're making good progress. But don't forget the modeling part needs to be to catch up with the fantastic data, and that's what we've been working on. And again, I just want to mention excitingly, if these black holes are in binaries, they could be hotspots for low frequency gravitational waves. And if they have some millimeter emissions, unfortunately, NGC 1600 doesn't, they are much larger than M87, some of them, right? But they're about equally more distant. So they could become good candidates for the next generation Event Horizon telescope, which currently can only target Sagittarius A star and M87. Okay, thank you very much.
Okay, thank you. Okay, thank you for the very interesting invited talk. So we have time for maybe one or two questions. Do you have any Slack?
Joel has a questions. What do you see in the Mitchell IFU kinematic maps for the galaxies that have no identifiable kinematic axis in the GMOS data?
Right, so there are two of them at the bottom, and really they just have no detectable coherent rotations. The V is so low, it's consistent with noise. If you don't have a rotation, you can't determine the axis. So there are two of them at the bottom.
Any other question? How much change in the black hole mass do you see if you apply triaxiality instead of the axisymmetric potential? Have you done any experiment?
That's a very, very important question. And I think it's going to depend on the galaxies. And so we have a big program going on comparing, for example, JAM's measurement, the genes anisotropy modeling versus axisymmetric short-shell modeling versus triaxial modeling. So refer to, for example, the latest 2693 paper, we have comparison. I mean, they can differ somewhat. I don't think they systematically go one way or the other. I don't think we have enough galaxies right now, to say, for example, triaxial always gives you higher or lower black hole number compared to axisymmetric. And but they can differ by some tens of percent. And we're working on the M87 black hole measurement, and we will let you know.
Okay, thank you. So I think that we need to end this session. Let's thank the speaker one more time. And